right, is everything visible?
Yeah. Well, so Zoom is showing us Michael with your slides, but we do see your slides.
Okay. All right, so I'm going to talk about our work verifying C++ at BedRock. And before I get started, there's a lot of contributors to this work. I just wanted to mention them. So I'm the only person giving the talk, but this is all work people who've worked at BedRock or are working at BedRock now or worked at BedRock in the past. Some of these people you might know. Am I lagging a lot?
How can we tell?
Is my audio terrible?
Yeah, it's fine. And it's somewhat in sync with your video.
Okay. I will turn off my video to preserve bandwidth, I think. We'll see if that helps a little bit. So just to set up kind of what we're doing at BedRock, we're verifying a hypervisor stack. That's the goal. The idea is to establish this bare metal property that basically says that we can run, that our virtualization stack acts as if it's bare metal. So this is the implementation, and the specification is really derived by physically disjoint hardware connected by copper wires and whatnot. And there's a lot of interesting challenges inside of here, but that's not really what this talk is about. What this talk is about is the fact that this whole stack down here is implemented in C++. And so a lot of people have talked about C today. I'm going to be talking about C++. They're not the same, but they're similar in many ways. And a lot of the problems that we see, verifying C++ code is similar to problems you would see verifying C code, weird things with pointers, integer to pointer cast, pointer provenance, and then just the nature of algorithms, things like intrusive data structures and stuff like that are things that are common inside of our code base. So for this, we've developed a tool called Brick. It's a C++ semantics. It's very similar. Much of the architecture of Brick is based on the VST style. So, where VST uses something like CLightGen to take C++ programs and produce representations in Coq. We use Clang, a tool called CVV that is built on Clang to take C++ programs and produces a representation in Coq. Our work is built on Iris. We've formalized inside of Brick the syntax that we generate from Clang, which is based on Clang's IR, but there's not a lot of transformations that are done in this. So it's very close to the source level. It does some things for us like type inference, inferring auto keywords. It does template instantiation and things like that. But there's no control flow graph analysis. There's no alias analysis being done by Clang at this level that we're leveraging. And so on top of this system, we've built automation. That's what's represented abstractly by this auto.v file. And we take these rules and we basically express them to our automation. And then when we go to verify a file, we will write a spec again in Coq, very similar, like I said, to VST. You write a spec, either pure C++ spec, this is separation logic, or you might write a model first. And then we do a proof by combining these things together. This proof is a tactic-oriented proof in C++, in Coq. I'll show you a little bit about what it does. And one thing that's interesting about our system, and I'll talk a little bit about the way it works, is we have a notion of hints that allow us to make this somewhat tractable. And I'll talk a little bit more about that. So the red parts here we could think of as being trusted parts of the system. So our semantics is directly an axiomatic semantics, and it looks something like this. These are some select rules. So I need to move this, but maybe I can't. So this is the rule that we see for the asterisk operator in C++. So if you're evaluating asterisk E as a L value, Then you evaluate E as an operand, as basically an R value. It must be a pointer, and then you have to show that that is a valid pointer and it's pointing to live memory, or not necessarily live memory, but memory that's live. It's a valid pointer basically, and then Q proceeds with P. So this is kind of what I would think of as being a relatively standard weakest precondition separation logic for C++. It's quite large, but these are, like I said, these are the axioms we're using. We don't have an operational model under the hood, so we're documenting these axioms based on appealing to the C++ standard. This is kind of the best we can do at this level. So some rules like this one are documented more than other rules, but all of this is publicly available. You can go to the GitLab webpage here, and the docs are published here. The docs contain extra discussions around the way we handle object layout and the way we do pointers and things like that, which are documented in the code, but also in the docs separately. There's questions we have there around how do we interoperate with assembly code and things like that. So, all right. So on top of the standard, or on top of the semantics, we have verification infrastructure. It doesn't really have a great name. It's currently mostly internal. I'm showing a little bit about how it works. So at one point in time, we did have our CPV2V tool would take Doxygen comments, parse them, and like paste them into Coq files that we would run in Coq. But we found that this, getting the writing things in C++ files and then generating Coq and running the type checker on those was a pretty bad experience at the level of tooling we had at the time. So we do write specs directly in Coq right now. We use this specify kind of macro, and we use long names here. So this is the specification of the initialization constructor for a point class, a very simple point class. And this is basically exactly what you would write in our tool. You can see we have this setup for using args. This is inspired by what VST has with pre-post. So we have things like arg that you say, I'm going to pass the variable x. We're going to pass an integer x, and the logical variable of that will be bound to x, which we have type z here. And then we have things like pre-post, which allow you to say, this will be a precondition and a post condition. It gets added in automatically. We found that that's really useful because lots of times you're passing in data structures and then getting out exactly the same thing. All of these things in curly braces are effectively with bound variables. And these requires our pure Coq side conditions that arise. So this is all open source. This is relatively reusable. And we've added a few more syntactic conveniences to it that I think make it kind of nice to work with. When you're using our tool, the verification is, as Andrew described, is done in Coq directly. You write a theorem that says that some piece of code satisfies the specification you write. And then you basically step through it with in the Coq buffer. We run an IPM. So over here, you see the goal. And down here, you can see where we are. So we're currently verifying a while loop, which is what you see down here with some of our printing notations in Coq. This is the context, what you have right now in your current state. Persistent stuff up here and non-persistent stuff down here. And we run tactics like WP while here is taking a loop invariant specified as a function call, basically, or as a recursive function. Actually, Michael Samler wrote the initial versions of WP while and tactics like that. So you can specify the loop invariant in the style, and you write it out kind of in the source code directly. Here's another one up here. We have a variety of tactics like this. The main driver for our automation is tactics like ego here. You can see a few of those, and those basically are kind of analogous to VST's forward tactic. It says, go as far as you can. Usually it'll get stuck at while loops or interesting if statements that might have join points, things like that. Yeah. And our verification infrastructure, kind of the smarts behind Ego, is based around extensible automation. So it's based around the idea of proving separation logic entailments, but interesting ones, things that involve WPs and whatnot, which are in our setup just separation logic assertions. The engine is very language independent, but we add in language dependent reasoning principles. And it's basically on the fly extensible in similar ways to what you'd see in probably in VST, or I know in refined C. So you can add domain specific reasoning principles to capture heuristics or reasoning principles for your specific class, and you can import those. And we have some great examples where we take kind of like a standard IPM style proof, which does a lot of stuff here. We're proving basically some atomic updates, and we can capture the reasoning principles there and some reusable hints, and then simplify proofs quite a bit. We've seen this for a lot of times for actual C++ programs. So we write an abstraction, like a collection or something like that, and then we derive hints that help us reason about uses of that class. There's a lot of features and challenges, I think, that occur, both on the automation side. People have mentioned things like performance and pure reasoning are big things that are important. Things like global variables, these are things that are kind of, let's see, in the math easy to do, but are kind of annoying to thread around through all your programs. Dealing with concurrency is obviously very important for us. Pretty much every program we verify and most data structures we look at are concurrent to some extent. On the semantic side of things, there's a lot of complexities, as a lot of people are aware. Pointers, type qualifiers, raw values, and memcopy. A lot of these have been brought up by other people, things like separate compilation and linking. Weak memory is not something we do right now, but is something that will likely rise in the future. And then C++ adds complexities like object construction, destruction, inheritance, and virtual dispatch, which we support for the most part, with some caveats. One thing that we've found in our application of this to our hypervisor is the nice, elegant specs that you would like to write for libraries aren't always, like, sometimes they end up putting more work on users. So when you go to use those libraries, it becomes complicated or kind of difficult, or verbose at least. One way we've been able to do this is by adding hints that kind of can take bigger steps through the automation or using the automation. But this is something that I think would be nice to look at in some of the examples we have, is not only verify a data structure, but use that data structure to verify something else, or maybe even two things. So you avoid over-tailoring specifications to a particular use that actually makes it more difficult to use in a general sort of way. So I think that's an interesting thing that has come up and is not always obvious when you start. I just taught us out a few caveats here. So C++, obviously, we're all aware, is not the same as C. It's bigger and slightly incomparable in the base layers. Another caveat we have right now is that our automation is closed source. I'd be interested in chatting with people about what you guys might do with it if it was open source. But we are a commercial company, and this is part of what we're working on. So if we were to contribute solutions here, one idea we have was to publish kind of like proof movies using the Electron system. We've built a few of these and they kind of look nice. Basically, it's a way to show you exactly what you get at every program point. Every time you run a tactic, you learn what is produced as the goal. So you can kind of step through the proof in a pretty nice way, actually, that way. But you're not able to actually run it on your own computer. You're not able to play with it, change it, because you don't have the actual automation that's underlying it. And I tossed out some evaluation challenges here, sorts of ideas that come up commonly. Intrusive data structures are one that's, I think, really interesting. But I think that's all I've got. So I'll stop now and take questions.
Questions? Comment?
Yes, thanks for the presentation. I was wondering about the evaluation. Like, since you're doing a lot of like actual like low-level systems code, do you have ideas for kind of like hypervisor kernel code or stuff like that, which could make good case studies, or something more in that direction? Or which kind of features maybe you would think are important for like this kind of low-level systems code for verification?
I mean, in terms of low-level stuff, I think a lot of what I think about comes from concurrency. There are some oddities, like our hypervisor plays a lot with weird address space layout. So like each core runs in a separate but a different but overlapping address space with other cores. So that's a complexity that arises. That's probably not something that is standard, but seems relatively common, maybe in very low-level systems code. And I think the question around that in C or C++ is very unknown. I think things that arise are things like working with shared memory across multiple processes. What is the right way to specify this? What is the right way to program against that is something that seems to be an unknown a little bit. This is very much related to IO sorts of behavior. Also things like connecting to devices. I think someone mentioned how do you program things like device drivers or interrupt controllers, things like that are very common in the sort of code that we're verifying. But we also are verifying application code. The hypervisor is that very small layer down at the bottom. And if you recall the picture, we've got several applications. We've done a lot of application verification on top of it. So scaling out in that way and having reusable libraries that are usable in many of these applications is also really crucial to us, which is why I'm thinking about things like collections and iterators and things like that, which are more common, I think, in C++ than in C, but are big wins in terms of productivity for developers.
So Greg, since you mentioned that you also verify application code, do you model both virtual memory and physical memory in your same C language? And how do they get connected if you do both?
Yeah, we model both of them effectively.
We lost Gregory.
I guess that was a commercial secret.
Maybe Brian Campbell intervened. He'll be back in a second. See.
Sorry about that. The mental model that we have, is that when a program starts, you get an allocated chunk of virtual memory that's kind of exclusive to you. And then you take that memory and give it to C++, and the C++ abstract machine starts running with ownership of that memory. But when we're talking about the connection between virtual and physical memory, we have assertions that are exposed that basically arise from the operating system, the hypervisor, things like page mapping assertions. So we can talk about both, this is the physical memory, so something like a p byte at, physical byte at, but we also have a notion of virtual byte at, and those things are connected and mediated via page mapping facts that are modifiable dynamically within the system.
Do you actually have an abstract machine model that contain both physical and virtual memory? Or do you have an abstract machine model only contain virtual memory for user level code? or like we kind of have to do those kind of things, right? Depending on whether you are verifying kernel level code or you are verifying user level code.
We don't have the same sort of operational machine semantics that you have in Certicos, but we expose this at the separation logic level, the specification of the operating system. And yes, it does contain, like I said, it exposes primitives like this virtual address in this address space is mapped to this physical address. And then we have assertions about physical pages. This physical byte contains this memory. So that's all exposed, but indirectly kind of through separation logic. And that's a proof that is in progress.
Great.
I've probably asked you this before, but what do you do with, if anything, with TLB invalidations?
We try to we have not yet verified TLBs and things like that. We talked a little bit at the Newton Institute about TLB invalidation, but those assertions need to, like assertions like this page is mapped to this address, need to capture the state of the TLB. So the page mapping fact for us will not be an assertion just about the state of page tables in memory. It will also need to talk about the TLB and caching that might arise in that.
Jason has his hand up.
Jason?
There's a question in the chat.
Yeah, I asked the question in the chat. So I'm wondering if you handle like generics in any way. And the second question is whether you have any ways to kind of make sure your C++ semantics is actually correct.
Okay, so the second question first, how do we know our C++ semantics is correct? I showed you kind of the way we've been doing documentation, or the way we've been trying to do documentation. So beyond that, we don't have any proofs that underlie it. We're really taking this program logic as the basis of trust for us. And it's basically a very pragmatic sort of thing. Like, as a company, our goal is to verify this hypervisor. That's an enormous amount of work. We're talking 50,000 plus lines of code here. And verifying our semantics against an operational one for C++. There are no operational semantics of C++ that I'm aware of that we could verify it against. We'd have to build that. Then we'd have to document that in the same sort of way. So we're kind of just skipping that low level piece. It'd be something I'd love to collaborate with people on, but it's not something that we as a company have resources to devote to right now.
Sorry, just as an aside, you don't necessarily have to do something that heavy in order to get a useful validation. I don't know if it's possible to extract from your WP definition something that you could execute on concrete examples.
I'd be very interested. We've been talking a little bit in the past about, or in the last month or so, especially about how we could evaluate the semantics. And if people have ideas on that, I'd love to collaborate on that sort of front. There's a lot of opportunities, I think. At least in my mind, I view separation logic as a very graphical medium. So, you could easily imagine rendering diagrams that show what memory layouts would look like before and after an instruction executes, for example. Comparing those, or comparing them to things like what might exist with Cerberus. But ultimately, it comes down to being able to interpret the documentation. And the C++ standard is about 1,700 pages, I think. Though a large portion of it is the standard library, which is not as important, but for us.
In practice, it may be more important to validate against Clang than to validate against that text.
Yeah.
Sorry, there was another.
True. Yeah, we do have to understand like how Clang represents certain things, but at least from what we've seen so far, Clang's AST at the level that we're working with it seems to be fairly close to the standard. I don't know if that's on purpose or by accident, but it seems fairly close. And also, I should mention that Clang handles certain things for us. Like if you pass C++ 17, then you might get a different parse tree, a different AST at our level than you would get if you pass C++ 14 or C++ 11. So some of that stuff that is changing in C++ is already taken care for us in Clang, which gets to the last point you mentioned about templates. We don't currently support verifying templated code before it's been instantiated, but we have verified the generated code, and we are interested in and working on a system for verification of templated code that does not add elaboration and template instantiation to our trusted computing base. We think that would be too much. So ways to reason about that code generically, but without adding elaboration to our TCB is an interesting challenge and something that is currently being worked on.
Okay, maybe we should move on to comments.
Mm-hmm.
Can everyone hear me fine if I shout at the microphone that's over there rather than turn on the ones here and which we hear it twice? So.
I can hear you fine.
Try sharing my screen. Where is it?